But this is our biannual or biennial. Every 2 years, I always confused. Once every 2 years, Theoretical Astrophysics Program Graduate Student Prize Talk. And I'm not sure how many more graduate students there are here. I see 2. But this is something that we'll try to make it a yearly event, because I think it's important to get to see and meet, our graduate students and what they do. But I'm very happy to say that this year the winner of the prize is Josh Lothringer.
Lothringer.
Right, there you go. It's no, but you pronounce it as an A, the opposite of my name. And it is, Josh is at the last year of his PhD. He came to us from the University of Colorado Boulder, where he worked on a number of missions, and I'm not going to try to say all of them because I will probably mispronounce it. He came here in 2014 at LPL, and he worked with Travis and Ian, who since has gone to different pastures. From us, and you're going to JHU, Johns Hopkins University, in the fall as a postdoctoral fellow there.
Yeah.
Which group are you going to work with?
David Singh there, Bloomberg professor.
Yeah, very good. So we have what comes with a TAP prize is a plaque for Joshua and a $500 check for whatever you want to do, but they wouldn't trust me with a check, so they just gave me the plaque. Right? I would probably lose it. But in any case, congratulations and thank you very much. And he's going to talk to us today about the extreme atmospheres of ultra-hot Jupiters. Now, since I know nothing about the subject, Travis is going to handle the talk and the questions, but yeah. And I'm supposed to press something. I'm supposed to press this.
Perfect.
That's the word.
Excellent. Yeah.
Go ahead.
All right, great. Well, thanks for being here. And thanks to TAP for the award and the opportunity to talk today. I'm excited to share with you my research on ultra-hot Jupiters. So it's a very exciting subfield of exoplanet atmospheres that has been emerging in the last couple of years that I will share with you today. So on the right-hand side here, we have a depiction of one of these ultra-hot Jupiters, an artist's impression. This one's of Kelt 9b. So it's the hottest known ultra-hot Jupiter. So it has a temperature of something like 4,500 Kelvin. So its black body flux actually peaks at about this color. So it's the only hot Jupiter that I know of that is so hot that its black body peaks in the visible wavelength. So it's orbiting a host star that's 10,000 Kelvin. So star's white hot, the planet's red hot, and there are a lot of interesting things going on in the atmosphere. So that's what I'll describe to you today. You'll only see the star alone, and so just before and after that eclipse, you can get an idea of what the day side looks like. So that's the way that we kind of disentangle the planet spectrum from the stellar spectrum. So the main observable there is the planet-to-star flux ratio, which I'll talk a lot about. So also want to point out kind of how unique these ultra-hot Jupiters are. So here we have planet mass versus equilibrium temperature for, I think this is all of the known transiting exoplanets around a star with a magnitude less than 14. So these are basically all the planets that we can characterize with facilities like Hubble Space Telescope. And you'll immediately notice 2 populations, Jovian and sub-Jovian exoplanets. So first to scale here, this is the solar system planets, so Earth mass is here, Neptune mass is here, so all these sub-Jovians are probably somewhere in between the 2. And then you have the Jupiters. I'd like to point out that these Jupiter planets are not necessarily the most common type of exoplanet at all. It's actually sub-Jovian exoplanets, but these Jovian exoplanets are easy to find and easier to characterize, so we pay a lot of attention to them. And they're actually some of the first that we've studied in detail. So here's kind of the region I'll talk about, which is the ultra-hot Jupiters. Here's Kelt 9, which was the picture on the front slide. It's the hottest known Jovian exoplanet. It's like 1,000 Kelvin hotter than any other Jovian exoplanet, just a ridiculous planet. But there are a lot of other interesting planets in this regime where I define it as anything greater than any planet with an equilibrium temperature greater than 2,000 Kelvin. It's kind of in this ultra-hot Jupiter regime. And these planets are interesting because they make really good observational targets. They're hot and bright. They have inflated radii, so they're a little bit bigger than your normal Jupiter. They have short periods, so they're eclipsing and transiting a lot. all of these make them really good targets for observation. And so we've invested quite a lot of time with Spitzer and Hubble and ground-based instruments to try and characterize these objects. And if you want to know anything more about these exoplanets besides its mass, radius, and the orbital parameters, you're going to want to look at its atmosphere. And so to do that, like I mentioned before, we take a secondary eclipse spectrum to try and determine what the flux ratios between the planet and the star are. And so that's what I'm showing here on the right-hand side, is the planet-to-star flux ratio as a function of wavelength. So this is the main observable in secondary eclipse. And as you can see, these data points are kind of representative of the data that we get. So we get a Hubble spectrum at wide field camera 3 at the near-infrared wavelengths, and then a couple of photometry points from Spitzer and ground-based facilities. So this is kind of the data that we have to work with these days. So what we want from these spectra are things like compositional information for these planets and the temperature structure. The temperature structure is going to be really important for telling us where in the atmosphere the irradiation and the heat is getting absorbed and where is it being emitted. So one of the very basic things you could ask about these temperature structures are they increasing or are they decreasing? So it's a very basic question. And if it's decreasing, we call it non-inverted, so it's just decreasing with height. That's kind of like the Earth's troposphere. But then if it's inverted, it's increasing, the temperature is increasing with height, not decreasing. And so there's kind of like the Earth's stratosphere. So the Earth's stratosphere is being heated by the absorption of short wavelength radiation by ozone. And so this is more analogous to Earth's stratosphere. And this has an important effect on the spectrum. If the atmosphere is non-inverted, then when you're looking at wavelengths of high opacity, you're sensing higher up in the atmosphere where you're cooler, so you'll look less bright, and you'll have these nice absorption features here. So this is like a carbon monoxide absorption feature. While if you're inverted, then in wavelengths of high opacity, you're still absorbing or probing higher up in the atmosphere, and you'll appear more bright. And so then you'll have a nice emission feature right here. So with these types of observations, we can tell if the planet's inverted or non-inverted. And this is actually predicted. Some of the first models of some of these hot Jupiters sought to see which planets were inverted and which weren't, and TIO was found to be a very important opacity source in these atmospheres. So you can see TIO in things like M dwarfs, where it's thought that in hot Jupiters, because of it's a very efficient short wavelength absorber, so it's able to heat the middle atmosphere to high temperatures, causing an inversion. So this is one of the first observational predictions that we had for exoplanet atmospheres. This is a proxy of pressure. Decreasing is with increasing height. So this is the top of the atmosphere over here versus temperature. As you can see, when you have a planet without TIO, you're decreasing with height, and when you have a planet with TIO, you have this large temperature inversion at about millibar pressures, tens of millibars. You can also see it here in pressure versus temperature. You can kind of see the transition between when you'd expect to be non-inverted and when you expect to be inverted. So the key here is that you expect to be inverted when you're hot enough that TIO is in its gaseous form. It's able to absorb the short wavelength radiation. Cooler than that, it's condensed and it won't be absorbing. And too much hotter than this, and you'll be dissociated. But there's this sweet spot right here where TIO is gaseous, and you can see that here in a plot of the partial pressure as a function of pressure and temperature, the partial pressure of TIO. And so when you're cool, you're condensed. When you're hot, you're dissociated. We're in the sweet spot between 1800 and 2500 Kelvin. TIO should be in its gaseous form and absorbing strongly and causing these inversions. And so this was one of the first predictions, and it's something that we actually thought we saw. So some of the early observations using secondary eclipse spectra or photometry with Spitzer indicated that at about 4.5 and 5 microns, the brightness temperatures that we were observing were a little bit higher than we would have thought from a non-inverted atmosphere. So this is for EG 209458b, the first transiting exoplanet. When we got this secondary eclipse spectra, it was interpreted as being inverted due to these high brightness temperatures. There were a couple other planets. One was XO1b. It was thought that this might be a very common feature in these ultra-hot Jupiters, was, or in hot Jupiters in general, was a temperature inversion. But it was found that not too many years ago now, actually, that the Spitzer observation suffered from intrapixel sensitivities. That actually, when you took those into account, these planets were actually not inverted. You moved the observations down from these gray points, they came down to these black points, which now your spectrum is consistent with a non-inverted atmosphere. And so kind of the discussion of inversions may kind of fell out of favor for a while, it fell out of fashion for a while, until we started to get some more observations of some of these hotter planets. And these have been indicating that we're actually starting to see these inversions again, and that they're not just an artifact from the observations. We're actually seeing something that might indicate behavior that we're not seeing at cooler temperatures. And the one thing that all these planets have in common, WASP-33 and WASP-121b, is they're all ultra-hot Jupiters. So they're all very hot. So these ultra-hot Jupiters are behaving differently than other planets at cooler temperatures. So one other indication that we had, so before some of those new observations that suggested inversions, we had our own evidence that we were seeing inversions. So this is just down the road, actually, at MMT. We were using the Ares infrared Echelle spectrograph to get high-resolution observations of one of these ultra-hot Jupiters, WASP-33b. So WASP-33b is a 3,000 Kelvin object, super hot. Before Kelt 9, it was the hottest Jovian exoplanet. And so we got high-resolution observations, and at high resolution, the planet is going around its star so fast that you're able to isolate its spectrum via Doppler shift. So we're actually able to identify the star and the planet as spectroscopic binaries. And with that, you can cross-correlate that with a template of molecules in its atmosphere and kind of detect certain molecules. And what we actually found was that carbon monoxide was in emission. So we added up 3 nights of this data and found that a nice cross-correlation peak, right where we expected the planet to be, indicating that the planet had CO in emission. So this was before we had a lot of the previous evidence, like I mentioned. So this was kind of confusing. We thought inversions were supposed to be rare. And for this planet, it was so hot that maybe there's some interesting things going on in this atmosphere, so we decided to model these planets. So I'll introduce them a little bit more. So ultra-hot Jupiters, in their eclipse spectra, they don't all have evidence of inversions. Some of them show features that are entirely absent. Others shows absorption features. So for example, WASP-121b has a nice water emission feature, but a planet at almost the exact same temperature, Kepler-13b, shows a water feature in absorption. And then WASP-18b shows a completely featureless spectrum. And so what we wanted to do was really understand what's going on here. So these planets, like I defined them, are anything greater than 2,000 Kelvin. They're great targets because they're bright, they're big, they orbit their host star very, very quickly. But what's important to keep in mind is that these planets are so hot that interesting things are starting to happen in their atmosphere. So molecules are starting to dissociate because it's so hot. Atoms are starting to ionize through thermal ionization. And you're starting to have this opacity from H-. So H- is an opacity source from when you have a atom of hydrogen in the presence of an electron. There's a bound-free and free-free interactions that cause a continuous absorption or a continuous opacity source that is actually non-gray. So it's actually varying with wavelength, but it's actually the strongest opacity source, continuous opacity source, at least in these planets. It's really important in stellar atmospheres, but we haven't really worried about that for exoplanets at cooler temperatures. And some of the examples of these ultra-hot Jupiters are, to me at least, household names like WASP-12b, WASP-121b, and Kelt 9b. So I want to point out how ridiculous Kelt 9b is real quick. So it's an example of an ultra-hot Jupiter. It's the hottest known, like I've mentioned, but it's orbiting its host star only 3 stellar radii away. So that's 10 times closer than Mercury is orbiting the sun. And it's orbiting a star that's twice the temperature of the sun. And the host star of Kelt 9b is twice as big as the sun. So you get 50 times more luminosity from the sun, and you're 10 times closer. And you're orbiting every 36 hours. So you end up with a temperature, an equilibrium temperature at least, of about 4,000 Kelvin. So all molecules have probably dissociated in this atmosphere. We think that because there's so many ions that the atmospheric circulation is actually, there's a lot of drag forces causing inefficient redistribution of heat. So this planet's probably more consistent with a day-side redistribution temperature of like 4,500 Kelvin. And like I mentioned, the lambda max here is 640 nanometers, so that's this like nice burnt orange color. So these planets are, like I mentioned, of course, super hot. So they're almost like stars in a lot of ways. And so to model that, we needed to use something that had a lot of the processes that occur on stars. So we use the Phoenix atmosphere model. So it's a general purpose 1D atmosphere model that can model everything from expanding supernovae shells to protoplanetary disks and giant stars and dwarf stars and irradiated planets. So some of the important things for stars and ultra-hot Jupiters are the fact that it has an expansive opacity database with data for opacities from the extreme ultraviolet to the far IR. And so, for example, Kelt-9, the host star of Kelt-9b, is emitting half of its radiation at UV wavelengths. So you need to understand what the opacities in the planet are at these wavelengths to understand how the planet behaves. It also has planet bound free and free opacities like this H- opacity that a lot of exoplanet models didn't have previously. So in this way, Phoenix is a very good tool to be able to understand these planets. Right. So I'm going to show you some temperature structures. This is pressure versus temperature for various planets. This is kind of a normal hot Jupiter. This is kind of similar to HD 209458b, maybe a little bit hotter. This is an equilibrium temperature of 1582, so 1600 Kelvin. And this is what we expect a lot of these cooler hot Jupiters to look like. You have your IR photosphere here bolded, so this is where our observations are coming from. So what you would sense is a non-inverted atmosphere where you would see molecular features in absorption. So this is without TIO, but if you add TIO, well, there's also a thermosphere here. But the thermosphere isn't occurring at your photosphere, so you're not really sensitive to that at IR wavelengths. So if you add TIO, your atmosphere is behaving very similarly. You're non-inverted at your photosphere. All your molecular opacities and opacity sources will appear in absorption rather than emission. And so it doesn't matter if you have TIO or VO in there. But when you move a little bit hotter, it turns out that it actually matters. So here's without TIO, and here's with TIO. And your photosphere, you actually have completely different behavior. You have this dichotomy of behavior, whether you have TIO in your atmosphere or whether you don't. So this has been known for a while. This is some of the early modeling that showed that TIO is important in this wavelength range, or this temperature range. But what we found was we're trying to model WAS33b, which is like 3,000 Kelvin, an equilibrium temperature of 3,000 Kelvin. And so when you push to even hotter temperatures, it turns out that you're inverted no matter what, whether you have TIO or whether you don't. You're going to be inverted at your IR photosphere. You have a little bit of a anti-greenhouse effect due to the TIO, but they're largely the same. And this was actually concerning at first. I thought something that was broken in the model, that how could you get an inverted atmosphere without TIO? Because for the longest time I had the two synonymous in my mind, that if you detect an inversion, you're detecting TIO, because there hadn't been a lot of discussion of other opacity sources that might be causing this. But it turns out it wasn't broken. This is actually a result, or one of the big results. So if you compare this with a star, just real quick, this is a stellar model from Sarah Peacock of a M3 star with a similar effective temperature as the planet's equilibrium temperature. And I just want to point out how different these objects are. They're similar temperatures at places, but for example, in the star, at 1/10 of a millibar, you're twice as hot in the planet as you are in the star. That's because obviously you're being heated from above in the planet, while in the star you're being heated from below. So while these planets can act like stars, they're also very unique and distinct objects. Okay, so here's what this is showing is the stellar flux as it's coming into the atmosphere versus pressure and wavelength. and to try and see where the what's being absorbed at what wavelengths. And so yellow means there's lots of stellar photons, and when you go from yellow to black, your stellar photons are being absorbed. And so what we found was, so here's TIO, where TIO would be absorbing, and you can see a little bit of absorption there, where you're absorbing at 100 millibars. And there's some heating due to that. But what we found was it was actually this region of the spectrum that's the most important, where you're absorbing a lot of this UV photons from things like metals. There's this forest of metals that hadn't been considered before, and that's what's driving the heating in these atmospheres, which I'll describe. So this is for a 3,000 Kelvin object around an F0 star, so there's significant flux coming in the short wavelengths as well, just because you're around an earlier type host star. A lot of the cooler hot Jupiters are around later type host stars, but these ultra hot Jupiters tend to be around earlier type host stars where you have more short wavelength radiation, and so this absorption at short wavelengths is even more important. Okay, so we want to connect what the opacities are to the temperature structure in some way. So what we do is we look at the mean opacities. So if you take the absorption mean opacity, which is the atmospheric opacity weighted by the mean intensity, which in the regions of the atmosphere where you're dominated by the stellar intensity, you could approximate that as the atmospheric opacity weighted by the irradiation, or the black body of the star. You can contrast that with the local Planck mean opacity, which is the atmospheric opacity weighted by the local black body function. And so these are basically telling you how effective is the planet at absorbing radiation, and how effectively is the planet cooling through emission. And so you're able to relate these two using an Eddington approximation, that the temperature in any layer of the atmosphere should be equal to the ratio of these two mean opacities to the 1/4 power times the equilibrium temperature. So if you were to plot this ratio versus pressure, you actually get behavior that looks very similar to the temperature structure. You actually see these kind of inversions, if you will. So this is temperature versus pressure, and the ratio versus pressure. And so what this is telling you is that when kappa J is bigger than kappa B, that's when you get these strong inversions. It's when you're absorbing more efficiently than you're able to cool. And so if you want to figure out why these temperature inversions are occurring, why you're absorbing all this radiation, you would need to look at the opacities that make up this absorption mean opacity. So that's what this plot's showing. So this is the absorption mean opacity, or the amount that the species is contributing to the absorption mean opacity versus the pressure in the atmosphere. This is just showing that iron is obviously very important in determining the heating in the atmosphere. While lower in the atmosphere, things like the resonant lines that are pressure broadened are important deep in the atmosphere once you've already absorbed all that stellar radiation. So right here is where your temperature structure becomes inverted. So it's a combination between magnesium and iron that's really driving this inversion in the first place. And then once you get to low enough pressures and high enough temperatures, you've ionized all your iron, and iron plus becomes the most important, with you're also dissociating molecules like CO and H2O, and its carbon also becomes important at higher temperatures. So this is basically what's telling us what's determining the behavior of these ultra-hot Jupiters. And so if you look at the volume mixing ratio of these species as a function of pressure, you'll see kind of what the other slide implied, that these iron and magnesium are important right where the inversion is occurring, but then they end up becoming ionized higher up. These hydrides are also important, but they're also rapidly decreasing in the atmosphere. SiO also plays a role at short wavelengths. Here's this H- opacity abundance. So this is very low compared to these other opacity sources, but it's such a dominant and strong opacity source that it's actually the strongest opacity source at continuum wavelengths. So here's more canonical species, things like H2 and H. Right at your temperature inversion, you're dissociating H2 and H. So your atmosphere kind of goes through a weird phase transition here, where you become molecular dominated at high pressures, and then at low pressures you're almost completely atoms and ions. So that's a behavior that we don't see in any other type of exoplanet. Even CO, the strongest molecule in nature, is getting dissociated at millibar pressures. Water, if you want to try and find water in these planets, you're going to be hard to find because you're dissociating it at tens of millibars. TIO, which people might have thought would be causing this inversion, is actually being dissociated at similar pressures. So it's obviously not TIO that's causing these inversions. Okay, so now we need to try and interpret, now that we have these models, we want to try and interpret the observations a little bit and see if they're consistent with our models. And good thing is that they are, at least qualitatively. So this is WASP-12b and WASP-18b, two well-observed exoplanets. You can see their wide field camera 3 spectrum and their Spitzer Spitzer photometry. This is planet to star flex ratio versus wavelength in microns. And we can at least match this qualitatively. These spectra aren't fit. These are just taking what we would expect from a day-side only redistribution model and a planet-wide redistribution model, and then putting TIO in and out. And what you get are these 4 models. They're actually able to fit these observations pretty well. You can get things like the absence of H2O. So the fact that we're not detecting H2O here is telling us that H- is moving the photosphere to lower pressures where water is being dissociated. So we're not detecting water in emission or absorption there, but that's not saying that the composition of the planet has to be weird. You're also seeing CO in emission, especially in WASP-18b. I think there's some phase curve data that's showing WASP-18b, you see the CO in emission on the day side, and then with the phase curve, you go to the night side, and the CO is now in absorption. So you're actually seeing the temperature structure change due to the irradiation. So that's kind of cool. So I want to talk a little bit about a paper that was actually on the archive today, where we want to take these ultra-hot Jupiters and kind of investigate a little bit more the role that the irradiation spectrum has to play. So these ultra-hot Jupiters are the most irradiated objects, Jovian objects at least, that we know of in terms of exoplanets. And so what the irradiation spectrum is made up of should be really important for how the planet behaves. So we took an ultra-hot Jupiter, we put it around an Earth-like star, a WASP-33-like star, and a Kelt-9-like star. So these are kind of representative of where we find exoplanets. And we wanted to see how the atmosphere behaves. And as you can see, this is showing the spectrum of the stars, and it's very different as you go from solar-type star to an A0-type star, obviously. So this is showing different planets around just different type host stars at an equilibrium temperature of 2250 Kelvin. And as you can see, when you have TIO, this is the equilibrium temperature where TIO and VO actually matter. It's actually determining your behavior. But when you're around an earlier type host star, your inversions are a lot stronger than around a solar type star. And that's just because you have more short wavelength radiation. So more of even though the total flux coming from the star is the same because your equilibrium temperature is fixed, more of your flux is at short wavelengths compared to a solar type star. So all that short wavelength flux is being absorbed by those metals that I mentioned earlier. And so you're driving even more heating in these atmospheres. And the same is true at 3000 Kelvin, where it doesn't matter if you have TIO or VO or not, you're going to see inversions no matter what. But around earlier type host stars, they're going to be steeper, you're going to have a larger maximum, and you're going to see a larger contrast in brightness temperatures. And so, as you would expect, these have important implications for when we go to observe these. So these are all observationally verifiable trends. So if you look in transit, so not secondary eclipse, but the planet passing in front of the host star, what you can measure is basically how big the planet looks at different wavelengths, telling you how much absorption is going on in the planet's atmosphere. And so that's what this is delta RP, so how the planet's apparent size is changing as a function of wavelength. As you're showing big CO absorption features here at 2.3 and 4.5 microns. And in the spectrum of a planet around an A0 host star, early type host star, you get this really large slope and a kind of muted feature. and that's due to H minus causing the slope and muting this spectral feature. So if you want to look at an ultra-hot Jupiter in transit, you might want to go after a planet around a later type host star, because then you'll actually see larger, more readily observable absorption features. The opposite is true, however, if you look in emission at secondary eclipse, because then you're actually looking at photons from the planet, and you're actually sensing the brightness temperatures. And as I mentioned before, if you have a larger inversion, you have a larger contrast in brightness temperatures, and so your absorption features will be correspondingly larger. So in a planet around a A0 type host star, your CO feature is going to be a lot bigger than around a solar type star. The same is going to be true if you look at high resolution, where you're actually able to measure the line shape. You're actually going to measure the same increased contrast for planets around earlier type host stars. Okay, so now I want to look a little bit towards the future. So there's definitely some open questions to think about with these ultra-hot Jupiters before we start observing them with James Webb or extremely large telescopes. So the first I'll talk about is the question of whether there's cold traps operating on high mass ultra-hot Jupiters. So this is an interesting question. So Thomas Beatty, who's here at Arizona, he's observed two planets, Kepler 13ab and Kelt 1b, that are both very high mass, so they're around 10 Jupiter masses. And both of them show an absorption feature for water, implying that their atmospheres are not inverted, even though they're at these ultra-hot Jupiter temperatures of 25 to 3,000 Kelvin. So this is really confusing because for almost the exact same planetary parameters, there's WASP-18b, which you don't see any water in absorption. So this is implying that WASP-18b is either isothermal or weakly inverted, but it's not inverted like Kepler 13 or Kelt 1b. So this is kind of confusing. So the interpretation for these high mass planets having a non-inverted atmosphere is that there's a cold trap mechanism happening. So there's not TIO. So in high gravity, you have more gravitational settling of TIO and VO when they become condensed. So you're sequestering them in the atmosphere so that then on the day side, when you're absorbing your radiation, there's not any grains to evaporate and absorb that radiation. So there appears to be some sort of cold trap mechanism happening, but it's only on some planets and not others, so that's kind of curious. Is it possible for this cold trap mechanism to happen on some planets but not on others? So there's some GCMs that people have run, kind of exploring this. It was one of the first explanations for why we weren't seeing inversions in cooler planets, was that there was a cold trap mechanism. So maybe this is still important at high mass. Okay, I'll also mention a way that we might be able to characterize planets in the future. So when I haven't been doing ultra-hot Jupiter stuff, I've been developing a retrieval algorithm. So it's the Phoenix Exoplanet Retrieval Algorithm, or PETRA, which is a framework. So we built a statistical framework around the Phoenix atmosphere model to be able to statistically sample the different parameter spaces to interpret observations. So what we do is we kind of take out all the fancy parts of Phoenix that can self-consistently model atmospheres, and we made it quick so that we can run tens of thousands of models in hours, so that we can fit observations. And the reason we're doing that is because Phoenix, we want to take advantage of Phoenix's extensive opacity database, its general versatility, and its ability to model things at high resolution and stellar and substellar objects. So one of the more ridiculous things you might be able to retrieve with PETRA is the non-LTE departure coefficients for certain transitions in high-resolution stellar observations. So that's something you could do with PETRA, at least theoretically, but that's not something other retrieval algorithms would be capable of. So I wanted to apply this PETRA to these ultra-hot Jupiters. So I had an idea that this H- opacity, since it's not gray, you're able to sample you're able to probe different areas, different pressures in the atmosphere. And so you can actually use it to constrain things like the compositional information or the temperature structure. So what I did was I took some simulated data, some James Webb data, from near spec. So this is about 2.2 microns to 5 microns at moderately high resolution of Kelt 9b. And then I fed that data to Petra and found that I was able to actually recreate the input temperature profile. So what this is telling us is that we can actually use H- as a novel way to measure and detect temperature inversions in these hot Jupiters, but also that we actually are able to get a measure of the ion fraction. So cooler planets, we're not able to get a direct measure of the electron density in these planets, but with H-, this is actually giving us a way to constrain that. So this is important in a couple ways. So first, for the chemistry in the exoplanets. So if we expect there to be a lot of photoionization in these planets. That's ionizing species down to millibar pressures, and that actually might be influencing the H- opacity. So we can actually get a handle of whether these planets are in equilibrium chemistry or whether we can detect photoionization. There's also the question of circulation. So these ions are also creating this magnetic drag force when it comes to the atmospheric circulation. And so actually getting a direct measure of the ion fraction plus the day-night temperature contrast, we might be able to say something about the drag forces that are occurring on these ultra-hot Jupiters. All right, I mentioned two last things just real quick. And one's atmospheric escape. So these highly irradiated close-in planets are going to be losing their atmosphere at least to some degree. And it's been detected, mass loss has been detected in a handful of these planets. So like WASP-12b has some detections of escaping gas. And so one question would be, to which planets we want to measure the mass loss rates in all these planets. And so with HST, with the short wavelength HST observations, we could constrain this. And same with CUTE observations. So CUTE is a CubeSat that is in development right now by people at CU that will observe several of these ultra-hot Jupiters at near-infrared wavelengths that might be able to detect and measure mass loss rates. So the other thing that I want to look at with these escape mechanisms is the fact that escape might be different in planets around early type host stars versus later type host stars. So around stars earlier than A3, you don't have your stellar interior is fully radiative, so you might not have chromosphere. So your extreme ultraviolet wavelength, your extreme ultraviolet irradiation will be a lot less for planets around stars earlier than A3. So that might be driving a different escape regime than for planets later than planets around stars later than A3, where you might be experiencing more EUV irradiation. So this is something that's directly testable and that we've described in Facade. The other question that I've kind of alluded to is circulation. So these high ion fractions can create these magnetic drag forces. So there's been some predictions that there should be a trend in increasing day-night temperature contrast with equilibrium temperature, where the magnetic drag forces becomes more and more important. But it's not really statistically significant in the observations yet. So we need more phase curve observations to determine if that's actually happening. There's also a question of MHD effects. A lot of these GCMs are run without considering magnetic forces self-consistently. But if you have a very strong ion fraction on one side of the planet versus the other, you might actually end up having a dynamo effect in the atmosphere. So this is something that might be changing some of the phase curve offset that we're measuring. So this is something that I think needs more investigation, is these MHD effects in global circulation models. Okay, well, I'll leave a summary up here. So I hope I've convinced you that ultra-hot Jupiters are interesting targets to observe, but we're just beginning to understand them. So James Webb and ELTs will give us plenty of good information on these planets, but we're going to need some strong modeling efforts to actually understand these planets. Ultra-hot Jupiters have temperature inversions. Once you get to a certain temperature, these temperature inversions are likely ubiquitous due to the presence of TIO, but also iron metal lines that are heating these atmospheres. ultra-hot Jupiters around early type host stars will probably have steeper and more intense temperature inversions due to the increased short wavelength irradiation and absorption. And also, we're now being able to interpret these spectra better because we understand that muted features can be from thermal dissociated molecules and H- opacity rather than any weird compositional differences in these planets. So with that, I'll leave my summary.
Thanks for the interesting talk. We have plenty of time for questions. Yes, in the back.
I was intrigued by something that you said about, you call it Petra, right? The algorithm.
Yeah.
You said that Phoenix is a slow code because of all the, large databases that it's using, and you said you really wanted to do it really fast in order to make it usable for fitting. How did you do it?
Yeah, so how Petra or how Phoenix will model an atmosphere self-consistently is it'll iterate on a temperature structure until you reach radiative equilibrium. In a retrieval algorithm, you don't necessarily have to make it in radiative equilibrium. All you're giving it is a defined temperature structure defined by some set of parameters and abundances. And you're seeing, does that spectra match the observation? So you don't necessarily need to iterate on it, but it's also a matter of taking out other things like other opacity sources that might be slowing the code down. So as maybe computational speeds can increase, we can add some of these fancy things back in, like different opacity sources or such.
I could just add one thing to that. So Phoenix is not generally that slow. The rate of transfer is extraordinarily fast. It's highly parallelized.
Yeah.
So we can take advantage of lots of cores. And one of the slowest things is reading in a molecular line list at the beginning and calculating the opacities. So once you're past that step, you're doing great.
Yeah. So yeah, once we can measure we can create a spectrum with something like 40,000 wavelength points. So that corresponds to measuring a carbon monoxide at a resolution of something like 500,000 or 250,000. We can do that in about a second. And so with that, in about a day, you can get retrieval to converge.
So at least one of those slides showed where the photosphere of the hot Jupiter was. What's sort of the reverse question? What's the typical depth in the atmosphere the solar radiation gets to before being absorbed?
Yeah, so it's kind of be shown with this plot. So this is showing the stellar flux as it's getting absorbed in the atmosphere versus pressure and wavelength. So it depends on which wavelength you're talking about, right? So your infrared photosphere is going to be here at maybe 100 millibar, but your near infrared photosphere is going to be something like a millibar. So yeah.
Maria?
I think Ben was actually first.
Oh, Ben then. Back up. Ben.
I don't know.
Ask
Okay, I just
first.
have a wild question that could we constrain the magnetic field of the hot Jupiter from the H minus? That is sensitive to those magnetic field?
I've wondered. Yeah. So I have to talk with some GCM people about exactly what you can do with the measurement of an ion fraction and electron density. It gets complicated because I don't think we understand those drag forces very well. But it will be sensitive to the magnetic field, yeah.
That's a good question because I think in the early days when star-plane interaction was kind of popular, people were looking for interaction between the stellar magnetic field and correlated with the planet properties. Now we're thinking about maybe measuring correlations of the planet properties with maybe the stellar magnetic field by measuring this. So it's good. You can come at it from two different ways. Now, Maria.
So I was wondering, especially for those ultra-hot Jupiters, you have these really strong day-night temperature contrasts and in general weak atmospheric circulation and stronger, you would assume to have stronger 3D effects. So do you have plans of accounting for that in your model? Because if, for example, the Feng et al. But it's not even looking at an ultra-hot Jupiter and
Right.
still showing that there can be significant biases.
Yeah, definitely. I think, so I know Tad and Shen Yu are modeling, trying to do a ultra-hot Jupiter GCM that hopefully will inform that a little bit better. How well is our 1D models fitting it? I think we'll definitely be impacted once we get some nice James Webb observations of I can almost guarantee you that our 1D models like won't fit then we'll definitely have to worry about it. I don't think anybody's models are going to fit then.
So actually there was an Origins talk earlier today that talked about another regime where Jupiters can get very hot, which is when they have, when they're forming and have these high temperature accretion shocks. I'm wondering if you thought at all about either how Phoenix could be used or whether some of the similar opacity effects might appear in that regime.
No, yeah, I thought the same thing. When I saw temperatures of thousands, several thousands, I started to think, oh, H minus is important there. And so, yeah, I'd have to read up on exactly what type of opacities are included in disk models. But Phoenix has the capability to at least give you a spectrum and a geometry from a protoplanetary disk. So you can, I think it would be worth investigating.
I had a quick question.
Yeah.
So when you mentioned that it was nice to have this little trip down memory lane about the changes in the Spitzer eclipse depths due to systematics, but I still noticed that oftentimes the Spitzer channel 1 and channel 2 observations are the most discrepant for the models.
Yeah. Yeah.
So I wondered if you've thought about, are the intrapixel corrections are they too aggressive, or maybe they just vary too much from the observations to even be accurate?
Yeah, I've heard a lot of people complain that one shouldn't ever trust channel 1, even nowadays. And so, I mean, things like WASP-12b, that there's no evidence that it's not inverted throughout the rest of its spectrum, but it's 2 Spitzer points to there are 6 eclipses that we've measured in each of these channels that measure it to be really low. And I don't know how you get absorption there.
Yeah.
You should be doing the opposite. So yeah, again, when we get James Webb Spectra, we'll realize how wrong everything was.
Can't wait. Any other questions? All right, let's thank Josh again.